All right, week 112. What's up, everyone? Welcome to week 112 of building my own operating system. Thanks for being here. Test 0 in the chat to get things started. Hey, Calf Flare with the test 1. Nice to see you, Calf Flare. Always first in the stream. I appreciate that. Nice. How are you doing today? VA 80, super punctual also. Test 2, we got the test 2 in the chat. Very good. Thank you. Cool. I changed up my color scheme. I'm using Dracula now. Calf Flare found my old kernel. Some user mode finally got GCC to become a lovely cross compiler. Okay. Calf Flare back in the OS dev, kernel dev era. So that's good. So chilling moments. Thanks for popping in. Could this be something in the near future that we can use? Probably not as a production OS, but maybe as like a educational OS. It's mostly a fun project. Yeah, it's mostly a fun project. But I think there is some useful stuff in here. Mostly if you are just interested in kernel development or operating systems and want to play around a little bit. Okay, I don't know why that was broken. All right. This would be a great educational OS. Thank you. I'm looking forward to eventually making some of it public. I think it is a pretty solid base. If you're just interested in playing around with some kernel programming, if you want to try doing a bit of page table programming yourself or interrupt programming or a bit of scheduling, I think what I built is a great base to do that on, which is exactly why I built it. So I'm impressed with the patience. Keep answering the same question every week. No problem. I would ask the same question if I saw some random person on the internet. This is an open source project, right? It is currently not an open source project. It is not, the source code is not public, except for the fact that I've shown so much of it on my screen. But that's it for the moment. So maybe it will be open source one day. But for now, it's a little bit simpler and nicer to keep it closed source. Okay. Let's kind of get into things a little bit. So we're out here, week 112. I'm pretty excited. I did some thinking this week about some cool stuff to do on stream today, and I think it'll be a pretty good one. You'll have to watch all the previous streams and stitch the code up. Yes, that is the way to contribute. You need to watch like 500 hours of video and type the code. Okay, cool. So we got a nice clean branch. I'm gonna get Algo to do that. Yeah, that's the real test. Okay, what's on the menu for today? Oh, dang. Number 1, this is on the menu. I had some ideas. I realized that I was doing something kind of stupid, I think, in my yield function, and there's a different way to do it. I was reading through XV6, which NSG had shared in Discord this week, and I was learning a little bit about how XV6 does things, and made me realize that I could simplify something. So we'll get into the details of that, but that's one. We're not going to use a naked function anymore for the yield. We don't need to do that. So we fixed the RF flags bug that That's done. Okay, this actually, isn't this really necessary? 6 does not do it this way. Okay, I've been refining my understanding of scheduling and stuff. So yes. All right, Tugra in the chat. What's up, Tugra? Nice to see you. Use blazing fast and memory safe Rust. Yes, one day. One day. What's up, Deepak? Want to build it in Rust? Rust is for normies. C is the way, and C++. Hi, Mark. Wow, so much has happened since I missed your live stream. I graduated, found a job in the defense sector, and currently working on USVs used an autonomous system for naval warfare. Dang, Tugra. Well, congrats on graduating, finding a job, and working on those kinds of important systems. I know it's a bit controversial, but I think that is important work that someone needs to be doing. So, congrats to Tugra, making the dream happen. So Pujith from India for videos. Thank you, Pujith. I was checking out your about page, saw you produce music. Takes me back to a bunch of my software. All of them produce music as well. It's a common intersection. It's a common intersection. Real quick, I don't use Rust just because I just don't know Rust, and I'm just trying not to overload my brain with learning two things at the same time. I'm just trying to learn one thing at the same time. Operating systems development. I can't learn two things at the same time, unfortunately. So I already know C++ pretty well, so I'm just using that for that reason. So Rob, what is your setup? Super quick. I'm just using Kimu. I'm using LLVM for the toolchain. I'm using VS Code. I'm using Tmux. I think actually, did I tools? I think I have a tools command. It's a little bit out of date. Using lazy git. All right. I think I'm just going to get into it. I'm just going to get started. So there's one thing. So the first task of the day. Okay, we got in the wrong file. So let's check out. Let's refresh our memory about what the kernel's looking like. So here's when the kernel runs. We go into the run method on the kernel class, and we start making some of the tasks that are going to run, some kernel threads, and you know what? That's actually not even the part I really want to show. But we're going to create some tasks, then start the scheduler. We're just going to schedule the first task, and then it never returns. That's why there's the panic unreachable. And then once tasks look like this, for the moment they are functions that receive a pointer to the kernel or a reference to the kernel. And for the moment they cannot really do anything. They can just do some computation. They can log some stuff. And they can yield to the scheduler. Lemony with the heart. Set up as in PC. Okay, my PC is a MacBook Pro. That's my PC. Did you know the person named Rumi who inspired you was my great-great-grandfather? He was Turkish. Rumi. I need to remember what exactly you're referencing. But there's like a philosopher. Did I post that on my blog somewhere? But what, your great-great-grandfather? Okay, Tugra, you got that philosopher heritage. That's pretty cool. Nice. Yes, sir. Week 112. Okay, let's check out the yield function though. Why this? Okay. So thank you, Mystic. All right, here's the problem. The yield function yields to the scheduler, but I did it in kind of a weird way. And I think there's a way I can do it way better. So the way I'm doing it right now is I made, like, my goal was to preserve the execution context of the task even before it really called into the yield function and just directly resumes from right there. And the way I did that was I made this, basically, I made it call directly into this assembly stub called assembly scheduler yield preserve task, which immediately offloads all the registers into a scratch buffer just because we need to save the registers. I think this is actually a bit more than is necessary. I think it's possible to optimize this a little bit by taking advantage of the calling convention and like callee and caller saved registers and stuff. But for the moment, I am ignoring that. And I just immediately just stash every single register basically, just to make sure I don't lose anything and just to preserve the state of the function of the program of the task, like really close to what it was even outside the yield basically. And that has some downsides. And so one downside is that I copy first into this global scratch buffer, and then back in C++, I copy that into the actual task state right here. And that's just like a little bit of an unfortunate design, like this double copy sort of thing. Also, this global scratch buffer is like a little bit problematic. So I realized, I think actually I don't need to be so paranoid about not using any registers. I don't need to be so paranoid about preserving the state, like really at the point of the yield call site. What I think I can do is make this pretty much a normal method. Normal method. And what I'm gonna do here, let me see. So basically the idea is running to, okay, I want to snooze the inline suggestions for 5 minutes. Going to get the current task, call the asm stub, pass the task as an arg. And it's just a small refactor, I think, but since the main difference is that with the stub right now, it doesn't really take an argument, which is why it uses the global buffer. I mean, I think it technically could take an argument, but it would be a little bit cumbersome of an API to do that. So let me just code a little bit. I'm just going to code for a little bit. I'll check the chat in a second and get to any questions or comments, but I'm just going to focus a little bit right now. So let me just quickly. So I'm just gonna code something out. So auto p task equals current task, assert task. A bit of this is in flux, and then we're gonna call the asm sched. Okay, I'm gonna. And this is going to take a task register state. So we're going to call schedule preserve task, and we're going to pass it a pointer to the ptask register state. And that is actually it. And then now in this code, pointer to task register state. So now this is a little bit different because now over here, and also I think the kind of a question is disable interrupts here. Maybe. I'm a little bit unsure if it is necessary. Like we could do it here, but I, in general, feel like it's a little bit cleaner. We want to be disabling interrupts immediately as soon as the task begins to yield. And I think we're just going to put it right here. So, which means I'm going to copy this comment and I'm going to remove this. And so now we have a pointer to the register state in RDI. And so I think we can replace all of those references to the global buffer with RDI. Let me just I think that's all right. So now we're going to be we're just saving, we're just basically freezing the state of the program right before this call, basically. And let me just think carefully. So RDI V880, I'm gonna work on my own project while watching you stream. All right, let's do some co-working. Sounds good. So we just need to be careful to not overwrite RDI. And we don't. We do it right here, but we just need to make sure we don't overwrite RDI until we're done saving things into the past task register state. And I think we are doing that correctly now. So now the difference is that we're no longer, let me just see if I can pull up the diagram. So what we're doing is, so previously the CPU has the registers. On the yield, we would first copy them into the global scratch area. That was the code that used to be here. And then after we return here into the yield bridge, we would then copy that buffer into the actual task. And that's what this arrow represents. And one of the main reasons was just because we didn't have an easy pointer to the task to save things into. But now that I've sort of refactored things to pass in a pointer to here to the stub, we can, this is what we've done. We're taking the CPU registers and going directly into the task, which means that we no longer need to do this part. Why am I getting yeah, I'm streaming right now. Is it important or what's not important? Okay. All right, my roommate just called me, but it's not urgent. Yep. So why am I getting a clang D target? I think maybe my clang D was pointed not at the right. There we go. Okay, cool. So basically now this yield bridge doesn't really do anything. It doesn't need to copy the state anymore. Its just job is just to go into the scheduler, which it does. and then it's going to select the next task and jump into it. And so I think that actually might really be all of it. So we just need to make sure, yeah, we just need to let me just double check. I think that should be pretty neat. So we're going to save. So what's going to happen is the task is going to enter the yield. It's going to basically get its state frozen. Okay, feel free to join me for the first 20-second break of today. Okay, the task is going to enter the yield. It's going to call yield. It's going to get its state basically frozen right here at the call sites of this assembly stub. And then when it's time to get resumed, it's just going to resume basically right after this stub call. And it's just going to exit the yield and just continue with what it was doing. So I think that is actually enough. Let's just run it and just see. I think that should, okay, I think that's what we were seeing last time. I think that actually just totally worked. And so I'm just going to, that's the initial easy refactor of the day. We're not totally done yet because we still have this global, where is this thing declared? The G context, whatever this thing is. And this thing is just never referenced anymore. So we can just get rid of this whole thing too. Okay, good. So that is a nice little easy win for today. Getting rid of that ugly global context buffer, at least as a start. So this is sort of inspired again by the XV6 way of doing things. Okay, then. Okay, cool. Okay, yep, got the stub there, so that's looking good. And I don't know, with refactor yield, remove global buffer. So that was a relatively easy fix. VA80 did 13 push-ups in 20 seconds. That is very impressive. Tugra says, once you're finished with the OS, I think you can move on to developing a robotics operating system. The world really needs a real-time robotics OS. Sounds good. Sounds good. Already Mystic, Brother Mark, I have just started my uni. Studies in IT and a basic web dev. Currently learning DSA. I am second year right now. How far am I to real world earning? Do you mean earning money? Well, I mean, it sounds like you have a pretty solid start. I mean, people in their second year of university already do get internships and stuff. I mean, the world has changed a little bit, but it sounds like you already have some basic web dev skills. So I think you could already just start getting out there into the world and just seeing, yeah, what kinds of what kinds of companies are in your area, or like what specific skills you could develop further. I mean, I know the job market's pretty hard right now, so you'll need to find an edge somehow, but I think you're on a good track. All right, sick. So that was a nice little easy refactor of the day. Done. Okay, done. Not so hard. We will probably still need to figure out some idea of per CPU global state eventually, though. Let's move on. So next thing, I mean, I think let's look back at the roadmap. So rflags bug is fixed. We refactor is no longer naked stub. Okay. Okay, let's just knock out a couple little small things while I'm looking at them. This is just another annoying thing. Don't store p context in the task, just store it in scheduler and pass to all tasks. And so I'm talking about how tasks get passed a kernel pointer on initialization. That happens because when you create a task, you pass it a context pointer as a second argument of whatever you want to get passed to the task. And I happen to pass a this, which is the pointer to the kernel. In practice, every single task is going to get a pointer to the kernel. There's no real reason to be passing custom context objects, really. So I think we could denoise this API a little bit. And instead of passing it to here, we just pass it to the scheduler directly. And so we're just going to pass in the p context, which means we need a m context, but it's actually an MP context because it's a pointer. So now that we have this context pointer that gets passed in to the scheduler, we're now in a spot where I think it even we're going to pass it in when we create a task. We're going to pass in the context pointer, I think. Let's just check out that diff. So we're changing this thing, we're getting rid of this thing, and we're no longer passing in this pointer. We're no longer passing in p context from the argument. We're passing in MP context, which is just a global piece of scheduler, or not global, but it's a piece of state stored in the scheduler itself. You know, I don't even, which means we can get rid of, we were storing a pointer here, and I don't even really know why. We don't need to do that. So yes. So, well, Marcus, nice to see you. How do you arrange your time to be consistent with your streams? So I will say I'm not completely consistent. I don't make it live every single week. There are weeks where I need to do it at different times. There are weeks when I'm traveling and I need to do a pre-recorded stream. But in general, for me, this is a pretty good time. This is like a Sunday. This is, and usually Sundays are pretty clear and free for me. I don't have a lot of appointments or things, and so it's not so difficult to just block the time and just plan to be at home and doing this. Also because it's important to me. So yeah, I'm pretty lucky though. I don't have responsibilities like caring for other people. So I have a pretty good amount of control over my time, and I'm able to make the time for it. At least for the current moment and this part of my life. So let's think about. Okay, so now we need to pass in this into the scheduler here. And what is, okay, so now the problem is we're passing in a PM context that's not necessary. Okay, cool. Cool. So just run the kernel. That looks good. So the current test that I'm running in the kernels, I just have 2 tasks that loop for like 100 iterations. And that's kind of it. And the tasks are just checking, they're doing a kind of particular check that the flags is preserved. And then they just kind of, after they do 100 iterations of that, they just infinitely loop and schedule between each other. So that's all I'm doing for the moment. It's super different doing software related with music and writing a software not related with music. I guess not much. I think, well, there are differences, but yeah, it's sort of both. It's like software with music. I mean, it is its own domain, and there are things that are unique about it, like dealing with audio, understanding audio formats. It can be very like kind of like graphics programming oriented often, where you're implementing like these interfaces for like making music. There's like real-time programming involved also, so that is definitely different from what I'm doing right now. There's a lot of things I'm doing right now that you do not need to do in music programming. So yeah, and Hello Code has joined us. What's up, Hello Code? Nice to see you. So I'm just kind of locking in a couple easy refactors. Move p context. Remove. Make p context global pass kernel to every task. I'm just doing some whip commits. This will probably get squashed later. Okay, so we just sort of locked in a second easy win for today. And shout out everyone who donated last stream. That was wild. People doing the donations for the first time ever on a stream. So now I'm thinking adding kernel exit, or adding kernel thread exit. For real, that was wild. That was crazy. This train of like 4 donations. Okay, added kernel thread exit. Yeah, I think that is sounding very intriguing right now. Just curious, was there anything else that okay, interrupts done. Okay, we have another roadmap even up here. Kernel exit, the idle thread. Okay, these are mostly the ideas though. So, Let's talk about kernel thread exit for a second. So what I'm trying to do is flesh out some more capabilities for my tasks, or like APIs that my tasks can call. Because like I said before, they can't really do very much right now. All a task can do is it can run, it can log some stuff, and it can yield to the scheduler. It can't even really exit. So I want to think about what that would look like. So honestly, I kind of sketched it out a little bit already. So the idea is, okay, let's say we want exit current task and yield. For example, let's say we want this to happen. Let's say we want them both to do 100 iterations, and then task 1 is just done. So it's just going to go away. It doesn't want any more CPU time, and we're going to leave task 2 running. And this is interesting because it's starting to do some, like, we'll be like allocating and deallocating tasks. So what's up, Ramakaka Duke? What did you study to be able to do this? I mean, I've just been coding for a long time, man. Like, I've been coding for like over 10 years. Longer even. I have a degree in computer engineering. And I'm just a curious person. I've just been learning constantly for like the last decade or more. So, but if you go back to my first stream, I did not know like any of this stuff. And so I've just done a lot of learning in the last 2 years just by streaming and just by teaching myself this. Obligatory shout out to the MIT course, which taught me everything I know too. And so we want to just exit the current task and yield, I guess. Maybe that's a bit wordy. To exit the current task, what do we need to do? We need to find the current task. We need to we need to free any resources that were allocated for the task. The only real resource right now is the stack. We allocated a frame of stack memory for the task to use. And I believe we did something sort of sketchy. Even we directly pointed the stack into the fizz map instead of mapping a stack. And so that was a bit of a problem. That's even something for the roadmap. Okay. So, but that's what we were doing so far. So basically now the key thing is we have this alloc here. So we need to do the opposite. We need to free the frame, and that's what we do here. We free the stack frame, and then we need to destroy the task. And so right now, again, I'm doing things pretty much as simply as possible. My tasks are stored in this ETL vector, which I'm still learning how to use. Let's just look at the ETL CPP docs. The embedded template library. Vector. Destroy. I'm gonna try a little bit to not use AI just to see if I can read the docs. Oh, excuse me. Access iterators capacity modifiers. So erase. That's what we are trying to do. I just want to so the question is the T iterator. H. So iterator. It's a T pointer. So let's see. Oh, we already hit the second break of the day. Feel free to join me. 20-second break. Be right back. Okay, push-up time. So the good news is the iterator is just a pointer to the type. And so theoretically, I should be able to do tasks.erase. That is an interesting suggestion. But I think it's not correct because we actually have the p task. So yeah. I think this is what we need to do. We erase I'm just going to do some logging here. So size of m tasks. Y, okay. Okay, so we're just gonna double check what the size of the container is after doing the erase just to make sure. I also wonder, I'm just out of curiosity, does it run destructors? It probably has to, right? So we have the iterator, blah, blah, blah. ETL move, I do not. Understand that, but it might not be necessary. I'm just going to ignore that. Destroy. Oh, it moves it to the back. Oh, I see. Destroy it. There's this function called destroy back. And so before. Oh, that's interesting and a little bit unfortunate. It actually does a copy. It like, I think it swaps the two things. Something along the lines of it swaps the element with the one at the back and then destroys the one at the back. Destroy at, so that's almost certainly going to run, yeah, destroy at, so it's going to run the destructor. So in case we had a more complex object, so let's just run the code. And as usual, what's the expectation? We're going to see 100 of those prints on from both tasks. We just gonna add a little thing here. Did print false if not. Yep, okay, it knows what I want to do. I just want to do one single print to signal that task to loop. And then when task 1 hits this thing, we're just going to see the thing about yeah, the task capacity, at which point one of these tasks could create a new task actually. So that would be kind of interesting to test. So let's just try that. Okay, kind of boring, but that's working. So size of tasks at 2 just erased, size of tasks at 1, task 2 is done, yielding forever in a loop. That's great. So so now we can think a little bit more closely. Like, this could be const, probably. Yep, could be const. And I have this comment, you could use a smart pointer instead. That is an idea. Right now, we are not really taking advantage of C++. We're mostly doing it C style, where we have an explicit allocation and an explicit free. And it would be interesting to, instead of having storing a phys adder, we would store some kind of phys smart pointer, or I don't know, something like that. And the physical smart pointer we would not need this, because when this task gets destroyed, it would automatically release the memory. So that's the idea. VA80 did 9 push-ups in the most recent break. That's still pretty impressive for 20 seconds, I have to say. And chat's popping off today. We got 34 people in the chat. That's pretty unusual. I gotta find a balance between chatting all day and making progress on my OS. But maybe we can reach a stopping point soon. I think we're pretty close to a quick pause point. So basically that worked. This is not a hugely important part of the roadmap, but phys smart pointer. Okay. I mean, this sort of seems to be working a little bit. But let's just double check. We just need to make sure we release all resources. The good thing is there's not that many resources to even release. All we do is allocate a task, allocate a stack, and we release both of those. Let's okay, so I'll do an initial commit kernel thread exit. So it would be cool to have some kind of test now that really exercises this a little bit more. Can we think of a good test? And so it's going to be something along the lines of like a dynamic, like kind of jumping back and forth. And so I think what I'm envisioning, task, test 0, I'll call it test 0. And so what I'm envisioning right now is, I'm just gonna not run those two things. I'm gonna run this. And in our test 0, what's something we could do? We could log hello from task 0. We let me snooze the inline suggestions for 5 minutes. We could yield. That is actually sort of interesting. What happens when a task runs off the end? Tasks should never really return. Yeah, tasks should never just fall off the end of the function. They should always end with a, I'll just call it exit. I'll just call it exit. Is that cleaner? I'll just call it exit. They should always have an exit. If a task actually like accidentally reaches the end, that's a bad thing. And the question is, what is going to happen? What does that mean? What's the diagram? So if the task stack starts here, I think that means that the task is like, so like a rip value usually. Right, so how does function calling work again? So what happens is you have a, I don't know where my, so let's say the stack pointer is right here. And then, so in normal circumstances, you have a stack and then you do a call instruction that is going to push a return value on the stack at the bare minimum. The function is going to run and do like all of its stuff, and at the very end, the stack pointer is going to be pointing right back here, it's going to do a ret and jump back to the return address, and the stack will get reset to exactly where it was. Now the question is, what happens in this case though? Because tasks are not really normal functions. Well, first of all, tasks are not really called into per se. Tasks are jumped into in a sort of like manual way, in a way that tasks are directly jumped into. So there isn't a call instruction per se, actually. I have a idea. I'm just curious to see what is going to happen here. My theory is that here's what's going to happen. So when we make, this is the normal case of like a normal function call. Like the call instruction pushes the rip, the function runs, and then the last thing is it rets and like jumps to whatever is here in memory. My theory is that with a task, we set the stack pointer to the top of the stack, and we just directly jump into some code. So there's no stack pointer that gets pushed. But the code in this test0 function doesn't know this. Let's actually, can we just binge this real quick? Let's just binge this. Let's look for test0. What? Oh, do I need to make? Yeah. Let me just try that one more time. So test0. Okay, we want the disassembly. So interesting. This is interesting. Does not return. Let's think about that for a second. Also, I'm just going to document what so the question is. So far, we haven't thought about that right here. And so here's the concrete disassembly, test0, logs and calls yield. And interestingly enough, there's nothing after the call to yield. And let's think about why that might be. You can see the CLI here. This assembly stuff also. Wait, I think, no. It does return right here. It just, something seems to sort of break the disassembler, and it seems to think this is a separate function. So let's go, how do I go back? I need to, okay, so wait, no, it totally does return. It just says does not return, but in fact, the return sequence is right here. So that was a bit of a red herring, but this is our assembly code for test0. Test0 does not, like when the compiler is code genning test0, it does not know that this is going to be invoked in a very particular way by an operating system. And so it's generating the normal sequence of code for the prologue and the epilogue, which contains a return instruction at the very end, which assumes, the return instruction at the very end assumes that thing that we were showing earlier. It assumes that 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 rip value would be here. In our case, the rip value is not going to be there because tasks don't get entered via a call instruction. They get entered via a jump ret sequence right here. All that means is that the rip is not going to be here, but the code, if the end of the function gets reached, it's going to try, even though the rip is not there, it's going to still try to ret to whatever happens to be in memory here, which is kind of bad. That is almost certainly going to crash. Probably the code that's going to be here is actually the first push is RBP. And so in practice, we're going to actually have an RBP value here. It's a pointer to the stack. And so what's going to happen is that the task will try to jump into the stack somewhere. And yeah, that's pretty bad. You never really know what's on the stack. And so that's not something we want to happen. And let me think about what we can do about that. So basically it's a bug. If something falls off the end of a task, that's a bug. Theoretically, that should never happen, but even though it should never happen, it's nice to build safeguards for these kinds of things. And so what I'm going to do right now is build a safeguard for myself, where I'm going to go out of my way to add a little bit of extra code just to safeguard against that case, and then basically crash in a more controlled way. And I think all we can do. Oh wait, I had a cool idea. So here, my first idea, number one, is we can preemptively push something onto the stack. We can push like an absolute, like guaranteed known, like garbage value onto the stack to ensure that the kernel crashes. That's idea number one. And let me just think about how to do that. So we just need to push. So let me think. So where's the stack pointer? The stack pointer gets set here. Ooh, RSP. So I mean, what we can do, push poisoned rip to catch bugs where a task accidentally returns instead of exiting. Cool. And so that's a good. I'm just I'm sort of wondering if that's allowed. I mean, we want to crash in any way, but also this is a very high address, so it doesn't really matter right now, I think. So what we're going to do, we're going to push. So RSP gets loaded here. We're restoring task. RSP gets loaded. Oh, wait a sec. No, this is wrong. this is the generic task restore. So that's the wrong place to solve this. What we need to do, it's more when the task is created, which is right here. I see. So what we need to do, it's right here. We need to, I'm going to snooze the inline suggestions. Write a poison rip at the top of the stack. I'll keep the comment. Okay, And so what we're going to do here, it's going to be something along the lines of, it's like RSP plus k page size minus 8 equals, yeah, let's just, which is also not an amazing number. Okay, and something like this. So we're going to basically RSP. Oh wait, no, RSP points to the top of the stack already. So all we need is RSP minus 8. So to be specific, so this is our stack. RSP is pointing at the top of the stack. Our goal is to write some dead beef right here. That way, in case the program accidentally returns, it's going to try to execute it's not going to execute to whatever's on the stack. It's going to try to execute dead beef, which should hopefully be unmapped. I have another idea to go even further with that, but that's just my idea. We're just going to, to do that, we take RSP subtracted by 8 bytes, cast it to a pointer, and then assign the value into that. So this should be kind of fun. So now to test this, what we're going to do is I'm just going to get rid of everything and take a 20-second break. Feel free to join me. Okay. Also checking the chat was good. JBTQ1LY. VA80 time to sleep. Thank you for joining. Sorry, I'm late for seeing that. Have a nice sleep. Yeah, all the credit goes to VA80 for the good chat today. Okay. So we're going to pretty much just not do anything. And okay, basic. So now I need to this is like just so wrong. Okay. Okay. We're gonna break on test 0. And we're just gonna step. We are in fact already pretty far into test 0. I'm going to just step a few instructions. So step 1, eyes over here. Step 2. So we're about to do the ret. And then now we should look at the stack. And we have some zeros. So that is unexpected. I was not expecting that. Let me dump some more of the stack. Okay, this is like, okay, I did something wrong. I did something. Why am I not seeing the dead beef? But it should still crash, but with a double fault. And what's rip? Rip is all zeros, that's why. I could even improve this message to maybe spell that out more clearly, but okay. So something went wrong there. Let me see what. I was pretty sure about that. So now what I want to do, I want to get a breakpoint immediately. Here, I want a breakpoint. Okay, so let's check out RSP. So RSP is this 53,000 number. And theoretically, if we look at RSP minus 8, we see the dead beef. So, oh, wait a sec. I think I know why. Actually, I think I know why. The dead beef, I think, got overwritten. Wait a sec. Wait, why is this incomplete? I think the dead beef got popped into RBP accidentally. I think what happened was our stack is here. So I pushed a value, I pushed the dead beef right here, but the stack pointer is still set to be here when the task exits. So as soon as the task does a push, it's going to clobber. And in practice, the task is actually going to pop, the task is going to pop whatever is slightly above the stack actually. So the bug is that if I'm going to push this here, I need to also make sure RSP starts here in the new task. And I'll do that. I mean, it's pretty easy. I just need to say, stack, task, stack, top, auto, sp equal stop minus 8. Yeah, no, but then here in the task, in this thing, we need to say RSP. So to get the top, we get, so we allocate a stack frame, which returns us the pointer, the physical pointer to the bottom of the stack. We convert that to a virtual address, and then add page size to get the top of the stack, which is the first out of bounds address. We subtract 8. Size t even even in fact, or size of void star, maybe, I don't know. T star. I mean, really, does this work? I'm gonna not overcomplicate things. I was gonna do it a size T star. Takes that minus the size of the pointer, write to this address, the dead beef, and then save this in the task state. So now let's run the kernel. And there it is. Rip, dead beef, dead beef. So that's cool. That's solution number 1. And all you get a GP fault that rip is dead beef. So that's better than just executing the stack, right? That's still not the best experience. I think we could do one level even better, where we just actually have a panic assert function that gets run. So here's the idea. Task. What's the name? Task returned without exit. And the AI knows what to do. Get rid of the task returned without calling exit. So in the most minimal version, what about this task or panic task? I'm using size T's in a weird way. It should probably be void star. But I think it doesn't really matter. So now let's run it again. And again, we're just running a super basic test task that just falls off the end. And if I did this correctly, we should see it panic with a very specific message. Yes, panic, task returned without calling exit. And so we're no longer passing dead beef, we're passing a very specific panic func pointer. We're pre-populating the stack with a function pointer that points to this function. And so if you ever fall off the end of the stack, it's going to jump to this thing, which will not actually crash, but it will jump to our very controlled panic function, which will panic instead of crashing. So that's a nice safeguard. What's up, James? Rip cows. Rip cows, what does that mean? Okay. So that's a nice safeguard. I'm pretty happy to see that, actually. So now let's think about how to actually do this a little bit more nicely. I'll maybe just ask the AI to size T. Oh, rip cows. I see. I thought you were making like a copy on write joke or something like that. Size E is a bit weird type to use here. Would void star be more idiomatic? I think it probably would be. Let's just Yep. So let's just go and keep the suggestion. I don't know, sort of tempted just to do this auto p panic funk. P panic. Panic funk. What's my naming here? It's a task stack top. It's P actual stack task stack top. Something like this. Okay, cool. So that's kind of nice. I don't necessarily want all of this. Okay, what do I want here? That's mostly what I wanted. Okay, cool. All right, let me take a quick stopping point for the chat, just in case anyone's still here. It's just demotivated me. Do not get demotivated. Do not get demotivated. Yeah, I think I missed some of these. When will you release your OS? I'm not sure when I'll release it, but if you are interested in seeing it when I do, please let me know you're interested by signing up for my newsletter. That's where I'm going to be posting updates about the release. All right. Cool. I answered some of these questions already earlier. The setup, you can check out my tools for the setup. I suggest programmers approach coding in the AI era. I think you should just keep understanding how computers work, but use AI to help you do that. Okay, so I'm liking this. So originally, the original goal was, oh, wait a sec, whoa, I just had an idea. So currently, we injected a panic. But what if we could inject an automatic exit, actually? That would be kind of interesting. I wonder, I'm just curious to explore that a little bit. So right now we just have this panic. But what if we could get called with a pointer? And I'm trying to, let me see. Okay. So tasks get past a pointer in RDI. And I think the question is that pointer still there by the time we return? I mean, currently, I'm not seeing anything that changes it, but if it was guaranteed that RDI would be unmodified. No, but that's not guaranteed, because what if we make a function call? We're going to clobber RDI. So I'm not actually sure we can do that in a super stable way. Let me ask. Can I copy an image into the? Okay. Is any state of RDI guaranteed at the end of a function, e.g. at the return instruction? If there was my panic handler that gets jumped to in case, all right, let me switch to in case a task automatically jumps or returns off the end, would be able to actually use that RDI value, which is a pointer to the kernel. But of course, if the task calls any other method, that's going to clobber RDI. So I just don't know if RDI will then get restored after the call. Can you help me clarify that? And it probably has something to do with the x86-64 system5 calling convention, I think. So my guess is that it's not guaranteed. Wait a second. Let me just, I just one test I want to do. So let's just say, let's just add some of this stuff back. So let's go back for the test. So RDI is the first argument, right? So that gets clobbered there. All right, 20-second break, be right back. Okay. RDI. But then RDI gets restored. And then RDI gets clobbered again because it's used as the this pointer for the scheduler. So it gets an offset of the scheduler. And then it's never restored. So that is just, that just means RDI is not reliably saved. And so I think the main point there is our only option, if we wanted to do even more, is we need to use the G kernel. There's a global kernel pointer, which we can use in situations like this. And so it could be like a warning task. Oh, what? I mean, maybe it's okay. Maybe this could be like just seriously supported functionality. Where you just like, if you don't exit, it's okay. It's okay. You can reliably just fall back on this handler here. Let's see about that. So what I'm going to do is, in order to test this, I mean, what's gonna happen is, if the only running task exits, the scheduler will probably panic. Let's just double check that. So if the only task exits, there's going to be no active tasks, which means that this thing, this mPolicy choose next task thing, is not going to find anything. It's going to return a null opt, and we have this assert, so we're going to assert. So here's the expectation. We're going to see hello from task 0. We're going to see warning task returned without calling exit. Then we're going to see an assertion failure. Let's try that out. Oh, we're actually seeing a boot loop or something like that. That is not what I expected. Let's step through that. So let's go test. Let's panic. So let's come here. And so we're here in hello from task 0, and then a return, and it's calling into this thing. And then now let's, we're gonna print out that print, and now we're gonna jump into exit. And there is a current task. It's the one that's currently on its way out. While I'm here, I'm also we need to be kind of careful about that. We got the current task still. P task, right? That's our task. Dang. Okay. I don't know how to list. When I press L, it is currently going more and more down. I just want to. That's annoying. Claude. I do L for list source. It keeps printing source out. How can I reset it back to the current rip? Does it know? Frame. There we go. Okay. Anyway, we're back at this thing. We're freeing. And then we're going to yield impl. And we don't have a current. Oh, do we? Interesting. So maybe that's a bug. And so the current task, what's a matrix coder? Let me get to you in 1 second. So the bug was that we exited the task. We go into yield impl, which calls current task. But we actually don't have a current task anymore because the one that was previously current is no longer alive. And so I think we need to actually unset this current running task index in the exit before we... I think we might need to do something like that. Because otherwise, what's happening here? We're trying to set... We're like getting sort of like a rogue pointer. We're setting something on it. And we call this, which did not, which found something somehow. Okay, that's also interesting. Oh, it found something because I guess we just marked it runnable. That's weird. It was not able to print out the value of the optional. So now we go into switch to task and dereference the optional. And I think that's what caused the crash. But that was super weird because it's like the assert didn't catch it. Let me break on... this is so annoying. Scheduler, round robin, switch to task, right? So we're starting at index 1, which is also not a valid task, and so we should start looping. For some reason, it's marked runnable. Current index. Runnable is 0, so I think it gets default. Things get default initialized to runnable. This actually, see, maybe that's actually bad. That's actually, I think, that's interesting. Tasks get like uninitialized tasks are actually, they look runnable because runnable is the 0th thing. Interesting. I'm just gonna take a note so to think more about this a bit later. So that's not good. Doesn't really matter though. So in this weird situation, we are now actually selecting task 1. Oh, interesting. So that's why I'm gonna return that. Oh. Okay, that's annoying. I cannot print out the value of an optional in LLDB. Okay, that's pretty annoying actually, but doesn't really matter. So let's go into switch to task. And so now if I step into, yeah, I see, okay. So now we have, now basically we try to jump into an invalid task that was never allocated. What's interesting is that we boot loop actually. Task causes boot loops, not a GP fault or a double fault. That is interesting to explore also. Okay, so real quick, so kind of in reverse order, let's make this, let's default things to not runnable, just to be a bit safer about that. And then in the exit code, let's make sure we did this. So now, if I run the kernel, let's just see what happens. It is still boot looping. That is pretty annoying. Why would it be doing that? So we erase the task. We set this to null op. We call into all this thing does is call scheduler.exit, which goes into here immediately. We technically still have a current task. It's sort of dying. We free everything. We unset the task index. We come in here. Oh, I see. We also, That's probably why. Because we unset this thing. All it does is cause this thing to not get set to runnable. So I think there's a lot of work to do around managing the scheduler state. But basically what was happening is we would exit the task. It would technically just remain in a runnable state and then get chosen, I suppose, and switched into. So this is real quick. So this should hopefully, no way. What is going on? Okay, things are not going my way today. I want to. It's also really annoying to. I'm just gonna save that. My clipboard. Okay, we want to break on a couple things. I mean, really just this panic task. So we're just gonna run there. That's where things kick off. We're gonna step into exit. We got the current task. We mark it as not. I'm just curious what P tasks. Okay, that didn't really work. So we unset. Oh my gosh, 37 people in the chat at the moment. I'm like most deeply not sure what's going on. That's crazy. Well, yeah, this is me just trying to figure out my scheduler. So I'm probably doing something pretty stupid. So so realistically, so we just erased the only task. I think the buffer is now empty. What's up, Lone Wolf? This is the most coolest live stream. I guess someone to. Well, thank you. I have no clue what's going on at the moment. Well, me neither. I'm so confused. What's up, Goku? I'm working on my kernel, my operating system. It is a baby operating system. It is not very far along. It's not very mature. And so that means we're working on the most important and exciting parts right now. Really essential operating systems types of stuff. And I'm wondering why things are crashing during like scheduling. Let me think this through a bit more carefully. So here's the flow. The stage of wondering why I'm doing what I'm doing. That is also true. Why am I putting myself through this right now? What is going on? So how do I debug this? I was in the middle of stepping through something, and so it just did it again. It boot looped. So let's just debug it. So we erase the task. We set the state of the scheduler to not have a currently running task. We go into yield impl. we do not find a current task. Which means it's time to choose a task from the tasks. And this thing is null opt. We do not have a currently running task. We just need to find a task. Okay, that means our search is going to start at index 0. Index 0. And we're just going to search through the tasks from index 0. Okay, it's not rocket science. Current index. Right? Oh, interesting. So already one issue is that I'm not really respecting the vector. I think the vector is technically empty, but I'm still going to iterate through it and access both of these entries twice. So that's kind of an issue. But even if it is an issue, these tasks are marked not runnable. Let's verify this. So not runnable. You can see the task 0, not runnable. We were just in it. We set it to not runnable. It's not runnable. So we're not doing that. We'll go to the second thing in the list. This thing is uninitialized. Why is it runnable? It's somehow that's still runnable. And let's think about that. So I initialize this thing. Oh, wait, what? It is, okay, the second task, there's an array of 2 tasks. The reason the second task seems to be runnable is because it's all zeros. This thing didn't matter. We never constructed something in that area. I see. So the bug is kind of embarrassing. Round robin scheduler policy. Here's the bug. We don't just blindly index in this array. We need to wait a sec. We need to just no, in tasks. That's all. That's what we need to do. We don't just index into the we don't just loop over everything up to the maximum possible number of tasks. We need to respect that we just don't know how many things are in the vector. So that is sort of a stupid bug. So now what we do is we just loop through the tasks and try to find and this is interesting. I mean, this could be so much better. What is going on? Wait, what? Wait, what is going on? I'm getting kind of confused. Wait, this is making less and less sense. So we have some tasks. Oh man, okay, there's a lot of problems. I'm just realizing. Calling erase, because it's a vector, calling erase invalidates all indices. So So this idea of keeping an index is pretty flawed. And now I'm starting to see why all these kernels use linked lists everywhere. Because those are much more stable. So I am discovering some fundamental problems with the scheduler, which is not surprising because I am just doing this for the first time. Let me record some of my learnings. So scheduler is flawed. What? Index of the current task doesn't work because erase modifications resize the vector and invalidate indices, and so this is why prod kernels use linked lists in part. Object stability. Whew. What's up? Pew Pew 2W, you made your own OS? I'm trying. It is broken, is what I'm finding out. But I am trying my best. Lone Wolf. So he is running a virtual machine on a Mac, and he making a kernel and compiling that kernel on that virtual machine. Is that what is going on right now? What's going on is I'm on a Mac. Yes. I have a virtual machine with QEMU. Yes. That's where the kernel runs. And I don't compile. Well, it's not really a virtual machine. I mean, it's just to run the kernel. On my Mac, I'm running a cross compiler, which takes in my source code and outputs a binary object that can run inside the emulator. So I'm not doing compiling inside the virtual machine. I'm only running the kernel in the virtual machine. So we are quickly kind of running out of time. So let me see how I want to land things right now. So just to zoom out, what I was working on is going into the details of what happens when a kernel task falls off the end. The first idea was, well, what was previously happening is it would basically try to execute the stack and it would probably crash. Our next solution was to just assert in that case. And our most recent idea has been to embed sort of like a safety landing pad that just calls exit and just calls the scheduler. And this mechanism works. We call into the scheduler, and what we're just finding is that my scheduler is just busted. I'm gonna kill the palm tree because we're getting close to the end of time. Okay, let me just think. So I think it's not that hard. We have this set of tasks. But this whole idea of the index, current index, is not really working out. Yeah, we could make it a linked list. Or we can't. It's unsafe to store pointers into a vector. So let me just try to do some really like YOLO coding in the last couple minutes of the stream. So we're going to use the ETL list. And let's just, yo, Afnan, what's good, man? You are late, that is true. You are here almost at the end of the stream, but as usual at the end of the stream, I am in a state of extreme desperation, which means things might get interesting, I don't know. And so I've just swapped out the vector with the list. But it's nice to see you, Afnan. Thanks for popping in. Hope you're doing well with whatever you got going on. And this whole concept is broken. So formerly we were having an index and then indexing into the vector. Let's not do that. Can we have a p current task? It's null pointer. And now's the part where I'm going to go current task. So this thing just, we just store a pointer. But the name is let me just see where else is this thing referenced. Okay, just doing some last inlines. Oh shit, trigger inline suggestion. Have you implement whatever? Which are you trying to do? Me too, I swear, me too. I hope I do it. Yeah, scheduler is the name of the game right now. And okay. So we are So what I'm doing right now is our scheduler, my scheduler or whatever, was previously done using indices into a vector, which is turning out to be a really stupid idea because you just do not want to be tracking indices into a vector. Vectors resize and they shuffle the elements around. And not only is that expensive to do that reshuffling, so that's a bad idea, but yeah, it also invalidates all the indices. And so we need to, I'm just trying to see if I can get rid of the idea of indices. I've been removing all references to the MO current running task. And let's see. And so this is going to look like, sorry, just sort of how I like to, we're going to get the p task, call it p next task. I'm going to pass in the mp current task. And switch 2 is going to take a p next task. Task p task. And it could even be a reference, even maybe a const reference. And now we're going to set the MP current task to this. This is just a task. Okay. We just got okay, it can't be a const reference. Watching someone using their brain is cool. Oh man. I appreciate y'all for tuning in. I'm just trying to use my brain. That's exactly an accurate description of what I'm trying to do right now. And I'm just trying to use my brain and not embarrass myself, but the ship has already sailed on that one. Okay. I'm removing uses of indices. I'm just using pointers. And so none of this like current task index equals task index. We're just going to track a pointer to the current task. And because we switched to use a linked list instead of a vector, once a thing is allocated in the list, the pointer to it stays stable. So that's great news. And let's just see. So I think pretty much the last place that is using indices now is this whole policy thing. So let's go into the policy. Oh, wise. Okay. Okay. So here, okay, here's the part where it's time to think. I mean, we don't need to be, we can, for the moment, let's just keep it kind of stupid. Although actually, I don't know. So what programming languages do you do this in? I'm using C++. All right. I feel like we're almost kind of close. I'm running out of steam a little bit. So here's a round robin policy. Choose next task. And okay, so we need to make this an iList. So we got the list of tasks. An iList is a thing, right? iList of tasks. We got a pointer. To the currently running task. And then now we just want to do some searching. And so ideally, we start searching from the next element. How do you do that? I'm just gonna ask the AI with ETL C++ library, if I have an ETL list and I have a pointer to an element in the list, how do I get the next element? There's probably some function, like some kind of next function to call. All right. Okay. Dang. Is this legit? Okay. This is getting down. Why waste the oxygen on iron oxide when you got jet fuel? Oh my gosh. Dang, this is not looking good. What do I do? So I'm running into some fundamental issues with my knowledge about how to use ETL lists for my linked list type. And conceptually, I want something and I might, man. Okay, let's try this. Am I missing something very obvious? You know, I really am not so familiar with what? Oh my gosh, how? Documentation, container, list. List iterator? Is it saying, can I construct a, this is public. Can I construct a list iterator from a reference to a node? Oh man, okay. I was in the policy. So, ETL, list, iterator, you know, I think I'm cooked. I think I'm cooked, everyone. What? It's the I list. This is underneath the I list. So maybe that's why. I list tab. Good call. Good call on the AI. You know, I'm just gonna try to get things a little bit compiling. I'm just gonna hard return null op. I'm gonna comment out a lot of stuff. I'm gonna comment out this entire thing. My goal is just to get something compiling. I'm gonna comment out this. I'm gonna comment out this. I'm just going to comment out this. What? Okay. So our okay, so I am so cooked. Holy crap. Okay, I think so. I think erase. I'm just going to fix me. I need to comment out some of these erase calls, I think. Cooked is better than burned. Of course, there's gotta be 48 people in the stream while I'm in my absolute worst moment of not knowing what the F is going on. Why? Okay, someone gotta tell me. Non-const cannot bind to type. What? Okay. Switch. I just gotta pull it together. Okay, that's okay. Okay, that is the reason. Remember how I was saying this thing? Okay. So we're returning null pointer right out of the gate, and I think, whoa, what just happened? Okay, we're back to compiling. That was whack. And the goal was seriously just to figure out. And then the question is, why doesn't this compile? What's going on here? So this is not valid, but I think I'm getting a bit closer. Yep. Sorry, I'm sort of fumbling around. So all right, time to whip out maybe a second AI. I did want to get going. I'm going to ask with ETL C++ library if I have a, okay, let me get this on screen. If I have a ETL list and a pointer to an element in that, how do I get the next element in the list, if any? Something with an iterator? Oh. What? Oh. Okay, so it's saying I need to do an iteration. That's pretty bad, or I can store an iterator. It's not a pointer, it's an iterator. That's also not ideal. That's crazy. Oh, okay. All right, I'm just gonna try to whip out the nuclear option. Temp. I'm just gonna clear things out. I'm just gonna, hey, okay. So I would like you to port the scheduler to not store a pointer to the current task, but rather store an ETL list iterator to make it easier to navigate around. Can you please do that? Okay, we're whipping out the vibe code. Otherwise we'll just need to pick it up next week. So the idea is, okay, I don't know what I'm doing, but storing a task pointer right here that is not working out, because apparently you cannot really navigate around in the list if you only have a pointer to an element. Somehow, so it's suggesting to just store a list iterator directly. Man, chat is going wild. Yeah, I think I'm yeah, I think I need to reconsider. We're gonna see what it does, and it's probably gonna be kind of busted, I don't know. And I need to learn how to use these types a bit more. I'm pretty confident that ETL is a good library for what I need to do. I just, yeah, so check up. There is the ETL intrusive list. That would be great. The reason I'm not using it is because I do not have a memory allocator yet, and ETL, the intrusive list, requires you to allocate your own objects. The thing that's nice about the regular list is that it already has its fixed buffer for objects, and so it sort of has this internal pool that it allocates from, and that's just nice for me right now because I just don't have a memory